Good evening. Am I audible?
That's right.
Yeah, thank you. We'll start the session in a couple of minutes. Wait for a couple of more people to join, hopefully, and we'll start it in 2 minutes. Okay, we'll get started with the classes today. So we are on week 2, where we'll be taking a look at the triangular duct problem. But before we go into that, we'll be looking at the graded assignments that were given to you last week. And the questions that I've shown here are taken directly from the NPTL assignment course. And we'll first discuss that, and followed by a discussion of the previous year question and the non-graded questions of the current week. And after that, we'll move on to an example problem, just like how we did last time. If you had attended that, I mean, it's very straightforward over here. So we'll get started with this. We'll get started with this steady state heat conduction equation with the source term for a one-dimensional form. And that is given by this equation: k into d square t by dx square is equal to q. And k is the thermal conductivity of material, t is the temperature over the slab or the wall or the rod or whatever is the system in study, and q is the volumetric heat generation. And we have to answer the question based on this information. So the first question is, for equation 1 to be dimensionally consistent, what is the unit of Q? Similar question was done last week in this session. And for that, we know that the unit of K is watts per meter Kelvin. We know that the unit of temperature is in Kelvin, and we know that the unit of length, if it is d square t by dx square, is in meters. Let's assume everything is in SI unit. So k into d square t by dx square should have the unit of joules per meter Kelvin second. This watts is the same as uh, joule per meter Kelvin second times the temperature divided by the length square. So finally, we would get the answer as energy per meter cube per second, and which is basically watts per meter cube. And this is what we'll be getting. The option D is the right answer. And if we, without even solving this, we can just identify from this term volumetric heat generation rate. So heat generation would be joules, rate would be per second, and volumetric would be referring to per meter cube. So with respect to one volume per second, what is the heat generation? That is what is asked. And we'll get the answer as joules per meter cube. Moving on, the second question here is, we wish to solve for a steady state temperature distribution in a rod of length L, and the variation is only axial. That means it's a one dimensional problem. And which of the following boundary condition is admissible? Now, when this question is framed, we have to consider uh, the problem in a CFT manner, not as an analytical solution. And we find that among the options that are given below, we have to assume that these are multi-correct options. So when we discretize, suppose we have a rod here. I'll put a new page over here. Yeah. Suppose I'm looking at the rod over here, where we have discretized this into uh, 5 segments, and we have labeled the points 1, 2, 3, 4, 5, and 6. And we are doing the steady state heat conduction equation d square T by dx square is equal to Q. And we solve this using CFD techniques. We'll be uh, doing this as k into T I plus 1 minus 2 Ti plus Ti minus 1 by delta x square should be equal to Qi. And when we apply this equation at each I equal to 1 to 6, sorry, I equal to 2 to 5, we'll get k into t3 minus 2t2 plus t1 by delta x square should be is equal to q1. Similarly, t4 minus 2t3 plus t2 by delta x square means k should be equal to q2. T5 minus t4 plus T2 by delta x square times k should be equal to Q3, and so on. When we discretize and write this equation in such a way, we can work with a condition that has both ends, that has when the temperature at the both ends is given. We cannot work when the heat flux at both the ends is given. Even when we do it analytically, we'll get it as we'll get the equation t in terms as q into x plus x square by 2 plus c1 x plus c2. So when dt by the heat flux refers to the temperature gradient at the points, and dt by dx at x equal to 0 and dt by dx at x equal to L. If these two conditions are given, we cannot find C2 here. It is not possible to find C2 here. So therefore, we cannot use heat flux at both the ends. And if temperature and heat flux at one end is the given, then again, if we do this way in discretizing this domain, we'll get a similar answer, a similar response where we will not be able to evaluate the second. But if the heat flux and one end and temperature at the other end is given, we will be able to work out an answer for this. So the answer is only A and D will have to come. Then for equation, moving on to the third question, we'll solve this by writing equation d square t by dx square is equal to q. And for this to be one dimensional, the term q can be of which form? Q should be a constant. That this is possible. If Q equal to constant, we can write the temperature as T equal to C1 x, sorry, Q x square by 2 plus C1 x plus C2. If Q is a function of x, again we'll get Q when you have to integrate Q dx times dx plus C1 x plus C2. Again, we'll get this form. If Q is a function of time, then we will have a problem, because we have assumed that starting we have assumed here in the first page where I said that it is has to be a steady state heat conduction, therefore q cannot be a function of time. So this answer is in fact wrong. Similarly, if again same answer goes for the fourth part also, q cannot be a function of time, because we have explicitly mentioned steady state problem. Moving on to the next question, which is an admissible extension of equation 1 to two dimensions. How can we take this and put it in a two-dimensional equation? So for that, we need to understand the energy conservation equation that can be found in any textbook, which has k times del square t is equal to q plus 1 by alpha times, I think, I'm not sure of the equation, but it can be found in any of the textbooks that can be seen where energy conservation equation uh, has to be used. So we'll find that this k is not multiplied for both the sides. Therefore, this is a wrong answer. So this cannot be one of the admissible extension of equation 1 to steady state heat conduction in two dimension. Whereas t if is a function of x and y, and we can write this equation as dou square t by dou x square plus dou square t by dou y square is a constant if the internal heat generation, volumetric heat generation is just 1000. But since we have all on the third, coming to the third point, again we have assumed that it is a steady state. So therefore, this third option is again invalid. So only two would be the correct answer over here. If there are any doubts, any questions, please feel to stop me and ask me. You can and ask in the chat box or unmute and speak. I don't have a problem if you want to interrupt me. Okay, moving on to the next question. We have an air-to-air heat exchanger, and we need to improve the performance of it by designing a better intake manifold, because the cold air is not uniformly distributed across the heat exchanger. Now, we wish to use CFD for this and arrive at a better design. And for this problem, what do you expect? Can anyone give me the answer over here? If you have already if you have already completed the assignments, maybe you would know the answer. Can I ask Maulin Rana to answer this? Yeah, it's basically very
Option A.
straightforward. Yeah, option A is the correct answer, because uh, when we are dealing with air-to-air heat exchangers, which directly uses, we are extensively using the energy conservation equation to design heat exchangers for getting for improving the performance or whatever it is. And we would not expect, this answer is wrong, we would be expecting CFD to be of useful here, and we don't have to worry about an analytical solution, and we would not rather do experiments if we are getting a good CFD result. So this option A would be the correct answer. Now, the same question has been given for a mass transfer problem. And if a reaction problem, there a client has produced a catalyst which would improve the rate of a catalytic chemical reaction, and he wants us to check it out. He or she wants us to check it out using CFD simulations. And for this problem, what would the necessary condition, what would we be requiring actually is what is asked. We expect CFD to give you a reasonably correct solution. That is correct, but provided the reaction rate is specified, because when we write the when we write the mass balance or change reaction equation, chemical reaction equation, we have to assume that dou rho I by dou T plus del into rho I ui should be is equal to Si, where rho I is the density of the species, and this equation is for mass conservation of ith species. Rho I is the density of species I, ui is the velocity of species I, and Si would be the rate in or rate of the reaction. So when it comes to the rate of the reaction, we would require a specific reaction rates, which is also known as the rate constant. And when we can look at the option C, we cannot expect, because chemical reaction cannot be handled through CFT. That is wrong here. And catalytic chemical reactions cannot be handled through CFT. That is again wrong here. So the option B would be the right answer. We need the reaction rate to be specified. Then we can move forward with the CFT technique used. Moving on to the next question, where we have asked questions about use of finite difference approximation for solving CFD problems. So the first statement is that finite difference approximation can be applied to problems described in cylindrical systems. Is that true or false? Can I ask Mr. Anil Banawat to answer the question? Anil is here. Can I ask Vinay to unmute and speak? Is the first
Option
statement
first, first,
sorry?
first option I think okay.
Yeah, first option is correct, because when we write the suppose let's take the velocity and write it in the cylindrical coordinates. This is dou square u by dou r square plus 1 by r dou u by dou r plus 1 by r square dou square u by dou theta square plus dou square u by dou z square is equal to whatever function of r comma theta comma z. When we are trying to discretize this, we can use second order differential here, and we can use the finite difference scheme here to find out equation for this setup, where each of the following equations are given by the as given here, ui plus 1. Yeah, I'll come to that. I'll just go one by one. Maulin, I'll come to your answer. Ui minus 1 jk by 2 delta x. This is the central difference scheme. Dou square u by dou r square should be equal to ui plus 1 jk minus 2 ui jk plus ui minus 1 jk by 2. This would be delta r, sorry, here. Delta r square. Similarly, we can discretize in the same way dou square u by dou theta square as ui j plus 1 k minus 2 ui j k plus ui j minus 1 k by 2 sorry, by delta theta square. There won't be a 2 here either. And dou square du by dou z square is given by u I j k plus 1 minus 2 u I j k plus u I j k minus 1 by delta z square. Therefore, we found that the apply problems can be described in a cylindrical coordinate systems as well. But for partial differential equation, there is only one correct finite difference approximation. That statement itself is wrong, because what we have done here everywhere is to use a central difference scheme as shown below, shown here. We can also use finite forward difference scheme, finite backward difference scheme, and then we can always change the given partial differential equation. So therefore, this statement is wrong. There is one correct finite difference approximation is wrong. Now, regarding option 3 is where some people would have a question whether finite difference approximation can convert a PD into a linear algebraic equation. Well, it converts a set of PDEs into a system of linear algebraic equation is basically what it does. And this system of linear algebraic equation is what is being solved in a finite difference scheme in CFD problem, especially for solving CFD problems. We solve a system of linear algebraic equations rather than just one linear algebraic equation. So that statement is also wrong. I hope that answers your question, Maulid. If there are no more questions, we'll move on to the next question, where we consider the Laplace equation in two dimension. In a two-dimensional rectangular domain with Dirichlet boundary conditions, the equation is discretized at all interior grid points using second-order finite difference approximations with uniform grid spacing in both the directions. Which of the following statement is true about the set of linear algebraic equations? So first we need to understand what is meant by the Laplace equation, and the Laplace equation is given by del square of phi is equal to some function of x comma y comma z. If uh, if f of x comma y comma z is equal to 0, then the Laplace equation becomes something known as the Poisson's equation. Now we need to understand that we are doing this for a rectangular domain with two-dimensional rectangular domain. So suppose this is our domain with Dirichlet boundary condition. We need to understand what is meant by Dirichlet boundary condition. Dirichlet boundary condition means the function value at 2 points is mentioned. This is known as Dirichlet boundary condition. The equation is discretized using at all interior grid points using second order finite approximation with uniform grid spacing in both the directions. So accordingly, we'll also have to yeah, we are also discretizing this domain using our finite difference approximation. Now, so if we are to solve this equation, and we'll get del square phi equal to 0, that means 5 dou square phi by dou x square plus dou square phi. Suppose we are taking the x and y coordinate system, we get dou square phi by dou x square plus dou square phi by dou y square will be some f. When we discretize this, we'll get it as 5 I plus 1 j minus 2 5 I j plus 5 I minus 1 j by delta x square plus 5 I j plus 1 minus 2 5 I plus 5 I j minus 1 by delta y square should be is equal to fi. So when we put all the equations, whenever we solve at any ith grid point, suppose let us consider this to be the ith grid point. So let us consider this as the ith grid point, this as the I plus 1th grid point, this as the I minus 1th grid point, this as the j minus 1 grid point, and this should be as a j plus 1 grid point. So we see that we are basically evaluating the function at or we basically want the values of the function at I minus 1, I plus 1, j plus 1, j minus 1, and I in order to solve this equation. But when we are concerned at corner points, if we are doing it at, let's say, suppose we have one more line over here, assume that this is all uniform, regardless of how badly I draw it. Assume that let's assume that this is perfectly uniform, where delta x and delta y are constants. So when we solve the grid point over the interior points, one to this 4 points, we see that we would require all the intermediate function values as well. But when we solve over here, this value and this value are already known because it's a Dirichlet boundary condition. So function value at here and here are already known. Function value around this point is known. Around this point is known. Around this point and around this point, these are all known. So therefore, when we substitute in each equation, let us assume we are substituting in this first point, we get it as I is equal to 1 or I is equal to, let's call this as 1 1 1 2 1 3, and 2 1 should be 3 1, and so for here solving it at I equal to 2 j equal to 2, we'll get it as 5 3 2 minus 2 5 2 2 plus 5 1 2 divided by delta y square plus 5 1 this would be 5 2 3 minus 2 5 2 2 plus 5 2 1 by delta x square should be equal to f 2 2 5j 2 2. So when we solve this, we see that 5 1 2 and 5 2 1 are all given by the boundary conditions as shown here. 5 1 2 5 2 1 are shown here. But when we solve for the interior points, we see that all five coefficients will be there. So therefore, my coming back to this, it will not necessarily have exactly five non-zero coefficient, but it will have at most five coefficients. So this answer is the correct answer, and there will be at least one equation with only one zero non-zero coefficient. That is also not necessarily true. That can be true, maybe coming to a particular case or something, but it's not generally true. So we see that if I equals to some interior point 4 comma j equal to 4, we see that all of these points will come. So each equation may contain 3 4 or 5 non-zero coefficients. So at most 5 is the correct answer here. moving on to the next question. We are solving a set of linear algebraic equations written in the form of ax equal to b using Gauss-Seidel method, and we are checking whether the method will converge on the conditions for which the method will converge. And first condition is if matrix A is non-singular, and non-singular means determinant of A is not equal to 0. The We'll move on to the second point, then we'll come and discuss the answer. The spectral radius of A must be less than 1. And spectral radius, does anyone know what the spectral radius is here?
Diagonal element.
Uh, Not exactly. It's basically spectral radius is the maximum of the eigenvalues of the matrix A. And our third point is matrix A is irreducible and diagonally dominant. And when what is meant by this irreducible means that there can be uh, excuse me, yeah, irreducible means that uh, no more raw operations uh, can be done to eliminate an entire row. So basically, when the rank is the lowest in that matrix, is what we call as irreducible matrix, and diagonally dominant. I had told about this in my last class, where diagonally dominant means that the diagonal element of each row is greater than the sum of the absolute values of other elements. So mathematically, this can be written as aii must be greater than sum of I not equal to j aij with the modulus. This is known as the strong form, and if it's weak form, it can be greater than or equal to I not equal to j aij. So, for coming back to the question where which we are dealing with, you need to check for the convergence criteria. So, if matrix A is singular, we know is non-singular. We know that an inverse of may does exist, but we don't. We are not sure whether an iteration method such as this would converge or not. This statement is actually not enough. Whether a matrix is singular or not, we'll just tell you whether it can be inverted, whether a solution exists or not, but it does not tell you whether an iterative method such as Gauss-Seidel will converge. The spectral radius of A must be less than 1. That statement again is not enough. So basically, what you are doing is you are solving Ax equal to B, and we are finding the xk plus 1 as let's say pxk plus q. Let this be p we call as the iteration matrix. So in when the true solution comes, we'll get that p. Uh, this should be x infinity plus one. And the infinite the after infinity iterations, we'll get the exact solution over here. So basically, the uh, I'll just rewrite this as pk plus one, where limit k tends to infinity. So basically what we are doing is we are just the spectral radius of this iteration matrix is what should be one, and the spectral radius is given by it's called as rho of A, and this rho of B should be less than 1. It's not the iteration, it's not the spectral radius of A, it should be the spectral radius of P that must be less than 1 for the method to converge. And for matrix A is irreducible and diagonally dominant, that is the necessary condition for the system to converge. If it is only if it is diagonally dominant, will the system converge? So among these answers here, non-singular matrix is not enough, not a sufficient condition to satisfactorily claim that the convergence criteria is satisfied. And spectral radius of the iteration matrix must be less than one, not the actually A matrix. And the third one is matrix A is irreducible diagonally dominant must be the necessary and is the satisfactory condition for the convergence criteria. Okay, moving on to the next question. Which of the following statements is true about the Gauss-Seidel iterative method for the solution of linear algebraic equations resulting from the discretization of the Laplace equation? Again, we know what the Laplace equation is. We have told about, we just introduced what the Gauss-Seidel iterative method does. So the method will always converge. That is wrong. We just need said that only diagonally dominant matrices will converge here. If it is not diagonally dominant, then it won't converge. Initial guess at one point is sufficient for the method to get started. And again, that is also wrong. For Gaussian iterative method, you need the initial guess at entire uh, domain is required. Not just an initial guess at one point is not sufficient. And the method will approach the exact solution asymptotically. That's correct. And this is because as k tends to infinity, as limit k tends to infinity, we see that xk plus 1 will actually become the true solution given by x to the. So option 1 and 2 are wrong, option 3 is correct here. So with this, we have completed the graded assignments for the first week. If there are any questions, I'll be happy to take them. Otherwise, we'll move on to the non-graded assignments that were posted this week. And this week dealt questions about the non-rectangular geometry, basically flow through a triangular duct and flow through an ellipsoidal duct is what is being there discussed in the non-graded assignment this week. So with respect to the, we'll start with the question. With respect to the figure shown here, for the given coordinate system where y is here and z is here, the governing equation describing the steady laminar flow through the triangular duct is given by which of them? So first we need to know what the Navier-Stokes equation is, and from that we need to reduce to this form. So what we can see is that the x-axis is the flow direction. Flow does not, right here in this case, you have to assume that there is no flow like this, or like this. There is only flow into the into the through the triangular patch. Yes, that answer is correct here. So when we discretize, when we solve this, We know that u, for a fully developed flow, for a fully developed laminar flow, we see that the we see that u is not a function of x and y. Sorry, u is not a function of x, whereas u is a function of y and z, because there will be variations along the y and z direction, but axially there won't be any change for a fully developed flow. And d square w by dx square plus d square w by dy square, if the flow was in the z direction, this could have been true. So option A is wrong, option B is wrong. Option C, d square u by dy square plus d square u by dz square is equal to minus dp by dx. That is the correct answer, as u is a function of y and z, and the pressure is varying across the axial direction. There will be a linear constant pressure gradient across the axial direction. And option D is d square v and d square w. Again, there itself, the Navier-Stokes equation is not how it is as shown here. So option C is the correct answer. Moving on, steady fully developed flow through the duct shown in figure 1 represents a balance between which of the following terms. So whatever we had shown in the previous question, d square u by dy square plus d square u by dz square should be equal to minus 1 by mu dp by dx. So what are the terms here? So I'll just rewrite this as mu times d square v by dx square mu plus u d square u by dz square should be equal to minus dp by dx. So what is the physical significance of these two terms? This is basically what is known as the pressure forces, and this is basically known as the viscous forces. For a fully developed laminar flow, we don't have to worry about the inertial forces. We just have to worry about the pressure and viscous forces. For an unsteady flow, we'll have a rho into du by dt. If it's not a fully developed flow, we'll also have uh, u rho times u dou u by dou x plus v dou u by dou y plus w dou u by dou z. This term will also come. Since it's a fully developed flow over here, we don't have to worry about anything over here. None of this come into the picture. So these two, for a fully developed flow through a duct, we are just concerned about equating the viscous forces to the pressure forces here. Okay. Moving on to the next question. For a steady laminar flow through a triangular duct, which of the following equations is applicable? I think this question was not there in the practice assignment, so I would ask you to answer the question first. Among 1, 2, and 3, which of the following equations are applicable? Is or are applicable?
First and third.
Yeah, that's correct. Basically, first is because this is just the continuity equation, which has to be valid because this is a mass conservation equation. And the third equation is known as the Poisson pressure equation, Poisson's equation for pressure. And del P is not necessarily equal to 0. It should be equal to a constant for a fully developed flow. So second option is correct. Wrong. First and third are correct. Okay. Moving on to the next question. For this domain shown here, the wall velocity is to be specified to be zero. Therefore, QR, the velocity at QR, QS, and RS is zero. How many algebraic equations would need to be solved here? What would be the answer? Anyone, if you have solved it, maybe you could tell me what answer you got. Okay, so what we are doing here is we cannot use finite difference method here. So you have to use finite element or finite volume method. And for finite element and finite volume method, what we do is FEM and FVM. We solve in the segments rather than on the points. So when we solve for the segments, we need to find out how many segments are there, and we see that there are around 16 segments in total. Therefore, each of these segments need to be solved and then found out. Uh, the answer needs to be found. Therefore, we still need to solve 16 algebraic equations here. Next, the vector form of uh, excuse me, the vector form of the governing equation for the uh, flow through an ellipsoidal duct is shown in figure 2 is what is the answer? We have to write the vector form here, that is the identity. So each of A, B, and C are actually the component form, not the vector form, component velocities, whereas option D is the vector form. And this del p will be something known as the tensor, and when we do that, we need to solve option D in order to find the flow. And but the governing equation for the flow through the ellipsoidal duct is given by option D in the vector form. Okay, moving on, suppose we need to find the velocity field in the ellipsoidal duct and we want to solve in the xy coordinate system. Which method would we use to solve for this velocity field? So basically, we discretize this domain in the xy coordinate system, and we solve for the velocities in each of these segments rather than the points here. We do that mainly because finite difference method cannot be used here, because mainly because we do this in segments rather than uh, in the points, mainly because the xy coordinate system cannot ensure the uniform spacing and all. So finite difference method cannot be used. We use either finite volume and finite or finite element method to solve for the velocity profile in each of these segments. Moreover, the coordinate system you cannot be the cylindrical, neither the cylindrical nor the xy rectangular coordinate system cannot be used here to uh, exactly solve and find out the values for finite difference method. Okay, we'll move on to the last question for the day, which is an example question. I have framed it on my own that I have taken this. I have taken the CFD course that Professor Srinivas Chinti had offered in IIT Madras. So this question was one question that was solved in the class during the lecture hours. So we have to consider the two-dimensional steady-state heat conduction equation, which we had seen earlier. or a modified version of it which you had seen earlier, given by k into dou square t by dou x square plus dou square t by dou y square. And we need to assume that uh, let's read the question first. In a wall of height 3 meter, length 4 meter, temperature at each wall is shown here: 30 degrees, 60 degrees, 70 degrees, and 40 degrees. Describes the domain into 12 square segments of equal area. Evaluate the temperature at all the interior nodes using Gaussian iterative method and estimate the residual after each iteration. Perform 4 such iterations. So, I just wanted to ask at this point if you are aware of what the Gaussian iterative method is. Yes or no? Okay. So, I'll anyway explain how to do the first iteration. After that, you can start your answer. If you want, if you already know it, you can start it. So, I'm just giving you a couple of other information. There is no heat generation anywhere. So, you can equate this to zero. It's all, the rest of them is already given. Steady state heat conduction equation. And we can, one more thing is the initial guess at all points. Assume that to be 50 degrees Celsius if you want. So what we have to do is we have to first discretize this domain into 12 square segments of equal area. So since this is a 3 meter and this is a 4 meter, we are going to divide the domain as 1 meter, 1 meter, as each segment to be of 1 meter length. And therefore each of this segment will be 1 meter each, and each of this segment also will be 1 meter. So all of this, totally there are 12 segments as given by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12. So therefore there are 12 segments and we need to solve for the temperature profile at each node. Therefore, how many nodes would be there? There would be 1, 2, 3, 4, 5, 6. These are the temperature profiles that temperatures that needs to be found out. What all is known? Temperature here, 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 and here. Everything is known. So let us start by discretizing the domain, or redrawing the domain as such. Let us let us assume this is the x direction and this is the y direction. Therefore, this point would be 1 1 and this point would be 5 3. So this would be 1 1, 2 1, 3 1, 4 1, 5 1. Similarly, here it will be 1 2, 2 2, 3 2, 4 2, 5 2, 1 3, 2 3, 3 3, 4 3, 5 3. Yeah, this is not 5, this would be 6 3, sorry. So this should be, no, sorry, again made a mistake. This should be 5 4 instead, right? 1 4, 2 4, 3 4, 5 4, 4 4, and 5 4. Yeah, sorry about that. So right now we know what the equation is. When we see even simplify this, we'll get the equation to be dou square t by dou x square plus dou square t by dou y square is equal to 0. Therefore, discretizing this, we'll get it as t I plus 1j minus 2 ti j plus ti minus 1j by delta x square plus ti j plus 1 minus 2 ti j plus ti j minus 1 by delta y square should be equal to 0. Let us start by putting these equations at the points I is equal to 2 comma 2. So we'll get the equation as t I plus 1 will be 3 2 minus 2 t 2 2 plus t 1 2 divided by delta x square plus, and rather than putting delta x, we know that delta x is equal to delta y should be equal to 1. So 1 square plus t 2 3 minus 2t 2 2 plus t 2 1 by 1 square should be equal to 0. Substituting the values of the known ones, which are t12 and t21, we'll get t32 minus 2t22 plus t12 in the question is, this is at 40 degrees, and on the left side is 30 degrees, right side is 60 degrees, and on the top is 70 degrees Celsius. So t12 would be 30 plus t23 minus 2t22 plus t21 would be 40 should be equal to 0. Yeah. Similarly, we would get the next set as uh, put I equal to 3, j equal to 2, we'll get t42 minus 2t32 plus t22 by delta x square plus t328. So it will be t33 minus 23 t32 plus t31 by delta y square should be equal to 0. So when we solve this, again we'll get t42 minus 2 t32 plus t22 plus t33 minus 2t32 plus t31 would be 40 is equal to 0. Let us call this as equation 1. Let us call this as equation 2. Again, I'm going to take a lot of time to solve all of this equation. So let's move forward very slowly. I equal to 4, j equal to 2, t phi 2 minus 2 t 42 plus t 32 by delta x square plus t 43 minus t 2t 42 plus t 41 by delta y square should be equal to 0. This was not clear. And here we know what is t41. So when we solve that, we'll get it as t phi 2 minus 2 t42 plus t32 plus t43 minus t2 t42, and t41 would be again 40 is equal to 0. T phi 2 is also not, sorry. T phi 2 would be 60, because we know that T phi 2 is the temperature over here. So T phi 2 is again now. Again, moving forward to I equal to, we just have to move from I is equal to 2 to 4, but j is equal to 2 to 3. So we get 6 equations here. So when we solve, when we put the next equation, we have to put it as I is equal to 2, j is equal to 3, and write the equation for that. T33 minus 2T23 plus, excuse me, T13 by delta x square plus T24 minus 2T23 plus T22 by delta y square should be is equal to 0. Now again, in this, what all are known? T13 is known, and yeah, T13 is known, and T24 is also known. So we'll write it as T33 minus 2T23 plus T13 is 30 plus T24 minus T2T23 plus, sorry, this this should be 70, and this should be T22 should be equal to 0. So this would be equation 4, this would be equation 3. Put I equal to 2, j equal to 4, we'll get, sorry, I equal to 3 and j equal to 3, we'll get T33 minus T43 minus 2T33 plus T23 by delta x square plus T34 minus 2T33 plus T32 by delta y square should be is equal to 0. From here, what all do we know? We do know only considering this point over here. We considering this point over here, we see that we only know T34. So T34 is known. We'll write T43 minus 2T33 plus T23 plus 70 minus 2T33 plus T32 should be equal to 0. This is equation number 5. Moving on, I equal to 4, j is equal to 3. We'll again get the equation as T53 minus 2T43 plus T33 by delta x square plus T44 minus 2T43 plus T42 by delta y square should be is equal to 0. I think we have the values of T53. Oh, sorry. I think we have the values of T53, and let's just take a look. We have T44 and T53. So we have T53 and T44, and T53 is 60 minus 2T43 plus T33 plus, this will be 70 minus 2T43 plus T42 should be equal to 0. Now we have 6 equations, we have 6 unknowns. So we can solve all of them together and to get the solution. So we just rewrite equation, each of these equation in a more simplified manner. So equation 1 can be rewritten as T32 minus 2T22 plus. Okay, and I'm just simplifying this a little bit more. I'm calling this as A, B, C, D, E, F. So that when when we write the equations in the matrix form, we'll be able to solve just it'll be a little bit easier to understand how to solve this. So we have to write equation 1 here, T32 to be, we are writing this equation as TB, or minus 4 times TA plus TB plus TD should be equal to minus 70. Then the second equation would be yielding us minus 4 TB plus TC plus TE should be equal to minus 40. Question number 3 would be minus 4, or excuse me, please 1 second, excuse me. Sorry about that. Question 3 would give us TB minus 4TC plus TF should be equal to minus 100. Question 4 will be TA minus 4TD plus TE is equal to minus 70, sorry, minus 100. Question 5 would yield uh, TD plus TF plus TB minus 4TE should be equal to minus 70. And finally, equation 6 would be TC plus TE minus 4TF should be equal to minus 130. Please let me know if you are able to get this matrix, or if there is any wrong answer that have been written down. Now we want to write these 6 equations in the matrix form to solve using the Gaussian iterative technique. We do that by writing the coefficients of each of these terms and writing the unknowns in the next matrix and equating that to the B matrix. We write it as Ax equal to B, where X is the variable matrix given by TA, TB, TC, TD, TE, TF. When we do that, we'll get the matrix as minus 4, 1, 0, 1, 0, 0, 1, minus 4, 1, 0, 1, 0, 0, 1, minus 4, 0, 0, 1. And the equation for TB would be 1, 0, 1, minus 4, 0, 0, 0, 1, 0, 1, minus 4, 1, 0, 0, 1, 0, 1, minus 4. We equate that to minus 70, minus 40, minus 100, minus 100, minus 70, minus 130. Now we have the form Ax equal to B. We need to solve this using Gauss-Seidel method. And Gauss-Seidel method, the answer xi for the k plus first iteration is given by bi minus sigma I sigma j less than I, ai j x j k plus 1 minus sigma j greater than I, ai j x j k plus 1. Sorry, this will be k by ai. So basically, what I've just done here is to write ax equal to b in a component form and just expanded that using this method. So what we need is an initial matrix x naught, or in this sense we would require t naught, and that is given by 50 everywhere, 50 comma 50 comma 50 comma 50 comma 50 comma 50. So we have an initial guess t at t at 1 2 ta tb tc td te tf is given in this form. So first what we do is, for the first iteration ta1 is given by bi, which refers to b1 minus j less than I. J is, I mean, here I is right now 1, so j is, there's nothing j less than I. Basically, this much. So, what we are doing is, let me just explain the steps first. We are finding out the answer for the temperature at the k plus first iteration using the temperature at the kth iteration. So for that to come, what we need to do is we need to subtract. Basically, what we are doing is we are just subtracting b minus aij xj and dividing it by the diagonal element over here. So Jacobi method does not have this term here. So whatever initial guess you are starting with, that only you have to subtract bi minus aij xj by aii. But for Gauss-Seidel method, what we are doing is we have already solved some of the temperature for till that j equal to I. We are putting that value here in this aij, and then we are solving it. So for the k plus first iteration, we are using whatever solved we have solved using the k plus first iteration, and then finding out the answer for the k plus first iteration again for the next I plus one iteration. So when we solve that, we will get TA1 as the first iteration. So for that, we need the iteration here. So we need the BI. BI will be here 70 minus 70 minus AIJ XJ. AIJ here would be 1 times TB minus 1 times TD. So all of them are 50 here. 50 minus 50 divided by AII. AII is here minus 4. So minus 4. So you'll get 42.5 degrees Celsius for the first iteration. Similarly, TB1 would be minus 40, because minus should be BI minus AIJ. AIJ refers to 1 times TA minus 1 times TC minus 1 times TE. Note that TA is calculated in the first iteration. So minus 42.5 minus 50 minus 50 divided by AII minus 4. We will get this as around 45.625. Similarly, TC at the first iteration would be BI minus 1 times TB at the first iteration minus TF at the zeroth iteration. So minus 100 minus TB at the first iteration minus TF at the zeroth iteration divided by AIL. Therefore, we'll get the TC as around 48.15625. Similarly, TD at the first iteration would be minus 100. That means BI minus TA at the first iteration minus TC at the first iteration. So that would be minus 100 minus TA at the first iteration minus TC at the first iteration divided by AI. We'll get this as 47.6640625, something like that. Now, TE at the first iteration, again, will be solving for this. This is minus 70 minus 1 times TB minus 1 times TD. Both are at the first iteration. Minus 70 minus TB at the first iteration minus TD at the first iteration. 47.664 divided by AI. We'll get this as 53.3222. And finally, TF is given by is evaluated everything at the first iteration. So BI minus 1 times TC minus 1 times PE. Everything validated at the first iteration. So minus 130 minus 48.15625 minus 53.322 by minus 4. And you will get this as 57.898696. So let us now tabulate whatever we have found out. Let's We'll have K, we'll have TA, TB, TC, TD, TE, TF. We'll just keep one more sentence. Excuse me. Let this be K, TA, TB, TC, TD, TE, TF. Here we'll calculate the residual. So when k equal to 0, we have assumed 50 to be our initial guess. When k is equal to 1, we found that TA is 42.5, TB is 45.625, TC is 48.15625, TD is 47.664, T is 53.322, and TF is 57.896. So basically, if we show this over here on what do you say, on the domain that we have selected over here, so we say that this is 42.5, this is 45 degrees, this is 48 degrees, this is 47, this is 53, and this is 57. You see that makes sense when you think about it. When the 30 is here, it's 42.5 is here. When 70 and 60, this is 57. This has the highest temperature among all the interior points, and this is the lowest temperature among all the interior points. So it makes sense physically also to while we solve this out. Now, what is meant by residual? There are multiple ways to measure this residual. One of the ways is to just measure. So we put this function, this equation into a times x. So suppose this is our, yeah, suppose this is our xk matrix. We equate xk minus to find out our bk. We multiply the a matrix that we have with the iteration with the variable matrix that we found out. Basically, we multiply this with the values here, and we found out bk. And we see that axk equal to, and we see that if bk is equal to the same as b, then we have exact solution. If bk is not equal to b, we have bk minus b, which is also given by a times xk minus b, which is known as the residual. Now, there are very various methods to measure this residual. What we see is we are having a vector here, or what do you say, a matrix here. A into xk will be a column vector, and b is also a column vector. So there are multiple ways to quantify this vector. One of them would be to calculate the 2 norm of this vector, which is given by the square root of the elements in this overall line. Square root of the sum of the squares, and we can eliminate, we can see how the residual comes out here. If you can calculate it over here, we'll get some value here. We see that after each iteration the residual has to keep on decreasing. There are there are various other methods also to find just sum of modulus of delta is also, yeah, sum of the, sorry for that, sum of the modulus is also there, sum of square root of sum of squares is also there. Another one is to just find out the maximum of delta of k. There are various methods to estimate this residual, and the and what residual we take based on our application. So in this question, you are free to take whichever form of residual you want to find out, and just note down the value over here. Similarly, perform 4 or more iterations to find the value of TA, TB, TC, TD, and TE and TF. And we what we should be arriving at is to coming to a steady state, or a steady state in the sense a value which converges to a particular uh, temperature or the profile over here. So we'll spend the next, I'll give you the next 20 minutes to figure out what the next T2, T3, T4, or TATB, TCT, TETF at the second, third, and fourth iteration is. And similarly, also to write down the value of the residual at each iteration. If you have any doubts, please let me know. I'll be around here. So I'll give you the next 20 minutes to solve this problem. So there is a question on how the equations is solved without taking determinants and its inverse. We are solving using the Gauss-Seidel iterative method. We don't need to find the inverse of it, where we just have an initial guess and move forward with the initial guess with the method that I've shown here. So we use this step without finding the inverse. That is the advantage of these iterative techniques. We don't have to actually find the inverse. We just can move forward with an initial guess and then solve the problem without using the initial guess. I hope that that answers your question. I mean, you can also do the inverse technique to verify your answer, maybe using MATLAB or something, where you can, if you are able to solve, if you are able to find the inverse of a 6 by 6 matrix, you can uh, verify your answers by after finding like the fourth iteration and checking the answers. You are verifying the answers using what you got from MATLAB.
Hi, good evening.
Hi. Do you have a question or?
No, I have general doubts, sir. So, can I ask some?
Yeah, yeah, we are discussing.
I'm very sorry I joined the session late, sir. I just now got home.
It's fine.
It's regarding the inlet conditions for nozzles, converging and diverging sections.
Uh, okay.
Mine is a theoretical doubt because I'm just not able to visualize how Mach number varies. I mean, the nature with which Mach number varies with respect to inlet Mach number. That is, if inlet Mach number is supersonic and we pass it to a converging duct, the exit Mach number is subsonic, or it is less than the inlet Mach number. It's not subsonic.
So suppose you are having a nozzle like this, where the flow is happening from left to right, or
Yes.
right. Okay. So you are your doubt is regarding the Mach number here at one and Mach number here at two.
Yes. Yes, sir.
So you, what is the question that you had? So your inlet would be subsonic, and
The
the
exit
out
will be
supersonic. Yes.
not supersonic, sir. It will be less than Mach number will be less than one because it's just a converging section.
Yeah. So velocity has to increase right over this region.
Yes, sir. But then if the inlet is supersonic, the
Uh,
Mach number decreases until one.
okay.
How is that, sir?
So Mach number is actually defined as the speed of sound in that area. I'll just write it out. It's defined as the speed of sound by the speed of fluid. Am I right?
I think it's the speed of fluid by speed of sound, sir.
Okay, I don't exactly remember this, but let me see if I can answer your question.
Okay.
So when the I don't think what you are saying makes sense to me, because if Mach number is according to what I've understood, the Mach number at one should be less than the Mach number at two, because since this is a converging nozzle section, the speed of fluid at the point one, and if you are comparing the speed of sound at V1 and V2, V1 should be less than V2,
Yes,
because
exactly.
yeah,
Exactly.
yeah.
What you're saying is true. But then, if V1, I mean, if Mach number at area 1 is uh, is to be at supersonic state,
Hmm.
then the Mach number will reduce. That's how the theory is framed.
Was I'm not sure. I was it from the lecture that was discussed.
It's absolutely from the lectures.
I am not entirely sure of why that statement has been made. Maybe it would have been a mistake. I'll
No,
just check
that's not
with.
a mistake. That is not a mistake. That is the case with
Okay,
every other textbook or every other theory that persists with regards to nozzles, diffusers, or even convergent divergent sections.
I see. I'm not entirely sure as to why that happens. I'll just check with Professor Srinivas Jayanti and see if I can get an answer for you in the next class.
Fine, sir. Thanks a lot, sir.
Yeah, sure.
And I missed the class today. So what happened earlier?
We were just discussing about we were the previous week's graded assignments, and yeah, basically all the graded assignments that were there for the previous week and the non-graded assignments that were posted this week.
Okay.
And also one example question on a basic CFD question on how to solve a two-dimensional steady-state heat conduction equation using Gauss-Seidel iterative methods.
Okay. Okay, sir.
You can get the recordings of the lecture by tomorrow, so you can view that to get how the class was done.
Okay, okay, sir. I might have joined the link for a different course.
Okay.
It is a mistake on my part. I
Okay.
apologize.
So what do you do? May I ask?
I am studying third year in mechanical engineering right now. I'm very much interested in CFD.
Oh, in
So
which
I
college? Which university?
Anna University, Chennai.
Okay. Okay.
So I wanted to do CFD, but then gas dynamics, jet propulsion, those Mach number, all those things interested me much. So
Yeah, actually, I am not actually that qualified to answer the question because we chemical engineers don't have to worry about Mach number.
yes, yes, yes,
I'm
yes.
doing my work on chemical engineering, so I'm not actually I'm not very aware of what's happening when
No,
during a
no, sir,
subsonic
that is a
supersonic.
blunt. That is a blunder from my side. I just did not see the mail properly.
No, no, it's okay. It's okay. It's fine. So yeah, I can get an answer for you. I can ask Professor Srinivas Jayanti. Yeah.
Fine, sir. And you are a master student at IIT, is it, sir?
No, no, I'm a PhD scholar here.
PhD scholar. Oh, great, sir. So I, you can consider this as general doubts or general advice if you can give me. I want to get into an IIT and perform, research fellowships or research uh, programs helping PhD scholars or even professors. What is the way to get in? I want to do CFD. CFD is one of my greatest.
Okay, then yeah, there are a lot of options available around these days. The first thing is you get a master's degree from somewhere and then come to an IIT Madras by applying through GATE, appearing for an interview and moving forward with that. Or you can directly convert your master's degree, MS, or whether it be a Master of Science or a Master of Technology degree, you
Okay.
can convert that to a PhD degree, just as how I have done it. I joined here as an MTech student by qualifying through GATE,
Okay.
and if the CGPA is well above the criteria, I mean, there's a CGPA criteria, but beyond that, there is no, uh, what do you say, difficult process or something. It's just straightforward. If you
Okay.
have that criteria, you can directly convert your master's to a PhD degree for a 6 year course. Yeah, MTech plus PhD, if you are doing it separately, it will take 2 years of MTech plus 5 to 6 years of PhD. Here, you
Okay.
can combine that to a 6 year course over here.
Okay. Is there any chance I can get in my bachelor's only?
You can convert your, I mean, I'm not sure of how you can come from your
Oh, research
bachelor's to a.
fellowships. I mean, if you are performing a research on CFD, I could probably help you or help.
Oh, you can come in as a project staff over here. You as an intern over here under a
Intern,
certain
exactly.
faculty. Yeah, you can ask. You can email the faculties whose profiles you have looked at, whether they are offering any projects. You can send a mail to them. They'll be happy to respond over here.
Okay, sir. Fine, sir. I've actually sent a lot of mails, but
I
I'll
mean,
probably.
if you are looking forward for CFT, maybe Srinivas Jayanti sir would be having some project or something.
Okay,
There are a
sir.
lot of opportunities over here. Even a lot of faculties in IIT Madras have opened up project staff positions for working in CFT. We go through the
Okay.
profiles of each of those faculties. I mean, I would say Himanshu Goyal, Professor Himanshu Goyal is one faculty.
I actually did mail a lot of professors. Professor Rajesh T, Professor Dipankar Das, Professor Vadlamani Rao, and
Yeah, yeah.
Professor
So you
Shantanu,
would,
Professor.
uh,
I did mail, but then I got no
yeah,
reply. Much.
yeah, I see. I mean, yeah, that's part of the deal when you have to send a mail to a faculty. You may not get a response or a
Fine,
appropriate response.
fine. I'll probably do that again.
Yeah, sure.
Fine, so that sums it up. And
Fine.
thank
Yeah,
you,
I
sir.
guess we'll be ending the session here as well. If you also don't have any questions.
Fine, sir. Thank you, sir.
Sure.
Good day.
Yeah, thank you. Good night.